Welcome to this Talks at Google virtual event. I'm Gabe Gaster, and I'm a software engineer on local search quality at Google. I studied math in college, but I only studied a little bit of physics, so most of my questions will be from the perspective of a mathematician and not of a physicist. Before we get started, I want to remind the audience that we will be taking questions toward the end of this talk. As you think of questions throughout this conversation, please be sure to add them to the live chat on the right. And with that, I am very excited to introduce today's guest, Tony Padilla. Tony Padilla is a leading theoretical physicist and cosmologist at the University of Nottingham. In 2016, he and his team shared the Buchalter Cosmology Prize for their work on the cosmological constant. He's also a star on the Numberphile YouTube network, where his most popular videos include a discussion of Ramanujan's sum of all the positive integers. Yes, you heard that right. Add up all the positive whole numbers, which has been viewed more than 8 million times. Tony, it is my pleasure to welcome you to Talks at Google.
Hi, Gabe. How you doing?
Good.
Pleasure to be here.
Good. Great. So I first heard of you when you were making the rounds on the internet for your video where you add up all the whole numbers. And as a way to introduce you in 2014, you sparked a massive controversy on the internet with your video where you show what happens when you add up all the positive integers at once. Can you share a bit about that video and the reaction?
Yeah, I love that you've gone straight in with the most controversial topic, Gabe, right? No messing about, right? Yeah, so it was obviously, so at the time, I remember when the video came out, I was actually in the US at the time. We were on holiday in Florida, and we'd gone to Disneyland, and maybe that's kind of appropriate for that video. And I guess I knew it would have a little bit of a reaction, but I mean, I just, as soon as it went out, and then I saw it all going a bit crazy on social media, and I was like, oh, okay, what's happened here? So yeah, there was obviously a whole range of reactions. I think it's a bit of a Marmite video. I had some people getting really, really angry. Well, lots of people getting really, really angry. Some people loved it. I think there's even one comment. If you troll through the comments, there's one comment on the video which even says, "I want to kill you," which I think is a little harsh. Just over, nobody should want to kill somebody over maths, right? But yeah, I think for a lot of people it was a gateway video as well into videos about maths. So that's the kind of the thing that I guess I'm most pleased about. So yeah, that's the backstory. But obviously, there's a lot more to talk about with this video.
Right. So I have a personal anecdote about that story, which is why I'm so excited you're here. So I have a few brothers. One of them is a medical doctor and one is a mathematician. And a few years ago, the doctor emails us asking, "What is this wacky math? Can this be really true?" And the mathematician brother, who was in grad school at the time, described the response on campus to the video. Most graduate students at the time, hated it. They had that visceral reaction. They would say, these people are wrong. They don't get it. They make math seem like total nonsense. My friend and old colleague, Kathy O'Neill, whose blog is Math Babe, said, if it's hocus pocus, it's not math. So one of the things, as just a backstory, one of the things that's drilled into people's minds when they're learning math at the college level is the concept of rigor. And I think the natural response of a mathematician to what you're doing is hostility, hostility. So I will say, though, that I'm sympathetic to the idea that there's alternate ways of seeing and understanding these concepts. But just as an example, I could do the same things that you did in your Numberphile video using the same maneuvers and deduce contradictions like 0 = 1. So what was different about what you were doing?
Yeah, so I think when you think of it that way, I think we presented it in a way that was meant to be for a sort of, a lay audience. And the result that the sum of the integers, well, we can debate about whether it's equal to -1/12 or whether it should be assigned a value -1/12. But that result is a robust result, which is used extensively in for example, in string theory and in theoretical physics in general. So the result is a robust one. The proof that we did, actually, yes, indeed, if you take some of our steps out of context, you can do things like what you've said. You can prove sort of nonsensical results. But actually, I have a little blog that I wrote where I show that every step that we did in that particular case can be mapped by a process called analytic continuation to a perfectly legitimate step. And so what that means is, and that's why we get the right answer, if you like, which is minus the 12th. It's not, I mean, if these procedures could give us anything, then we could have come up with anything, right? So, but we actually end up with the right answer. So that's not a complete fluke. And so you actually, there's this process of analytic continuation where you can map a sort of a function, analytic function in one sort of complex domain, in one area of complex numbers, and then you can sort of, you know, map it to another region and use the results to extend the definition. And that's the trick that we were using, really. But there's an awful lot to say about this. There's an awful lot, I think, that people sort of say and assume about this sum of the positive integers, that based on a lot of prejudice, actually. So one of the things people say, for example, is that, well, you're throwing away an infinity, and people think very much in terms of finite intuition. So, for example, when people say, well, the sum obviously just goes up to infinity, and it's clearly true that if you take any finite, you know, take the first billion integers and add them together, you're going to get a big number. If you take the first trillion, you're going to get an even bigger number, and so on. It's going to grow and grow and grow. No one's disputing that. But that's a very particular way of regulating the sum, right? It's a very particular way of doing it. In fact, it's a very sharp way. What you're doing is I'm taking the first n, and I'm going to cut off n plus 1 and beyond, right? And I'm not going to include them. And I'm going to see what happens as I get n bigger and bigger. That's a very sharp way to cut off that series. But the reality is it's an infinite series. It's got an infinite number of numbers. And actually, there are different ways you can do this. You can have more smooth cutoffs. And when you cut this thing off and try to regulate it in a smoother way, then the minus a 12th emerges much more naturally. And you don't always get an infinity. Sometimes you can get it without one. And that's what's really incredible. And this is some really interesting work that I'm looking at with a PhD student at the moment.
Great. Okay, so you're also here because you wrote a book. I got it right here. Fantastic Numbers and Where to Find Them. And so, you know, for starters, why did you write this book? If there was somebody, you know, reading it, if there was like an imaginary audience that you had in mind, an imaginary reader, who was that person?
Yeah, so I've always wanted to write a popular science book. So I lost my mom quite recently, and I was looking through some of her things, and so a few years ago I'd written, I did like a sort of story of my mom and dad's life for their golden wedding. And I saw a little note she'd written to her brothers and sisters saying, oh, you know, Tony wrote his book, and it sort of brought a tear to my eye. But I always knew he wanted to write a book, but I assumed it would be some obscure physics thing. So I guess what this book is the obscure physics thing that she'd anticipated. So in some ways, the book is for her in that sense. But yeah, actually, so what happened was I was actually the friend of mine, another person who the book's for was actually poorly with cancer, and we were trying to raise money. So I started giving talks, sort of related to some of the ideas I talked about in some of my YouTube videos, things like a Googleplex, Graham's number, that kind of thing. And we were raising money in some of these talks, and then I realized that actually this talk, the content of it would sort of turn very naturally into a book. And that was really the seed, and that was sort of just before COVID. And then of course COVID hit, and I had, you know, homeschooling to do while I was writing the book, which was a lot of fun. So yeah, if I had to say who the book was for, I would say it's for my mum and my friend Hendo, for whom we were raising the money originally.
Right. Yeah, I read that in the acknowledgements. That's great. So in your book, you discuss a Googleplex, and we wouldn't be the company we are if we didn't take a moment to pay homage to the misspelling of our namesake. So our audience might know that a Google is a giant number. That's the number 1 followed by 100 zeros. And a Googleplex is a much, much greater number. That's 1 followed by a Google zeros. Our audience also might know that the company Google was named for this number, though it was hilariously misspelled. The number ends in OL, and the company ends in LE. And so you use the occasion of a Googleplex to talk about the concept of our doppelgangers. Can you describe that for us?
Yeah, so I mean, I think the history of the Google and the Googleplex is really nice as well. As it goes back to Edward Kasner, who was a physicist at Columbia University, and he was actually writing a popular science book. So a few of us have done that, and he was talking about infinity, and he really wanted to sort of explore the idea that infinity's any finite number you take, no matter how seemingly large it would be, is tiny compared to the infinite, negligible compared to the infinite. So he came up with this idea, well, what's a big number? What's a number that everybody agrees is big? Well, it's going to be a 1 followed by 100 zeros. So he needed a name for this number. So he actually consulted his nephew, who was 9 years old at the time, and he was called Milton Sirota. And he said, well, can you come up with a name for this? And Milton came up with a Google. So that's where it originated from, the name that your company is now named after. And but Carlson didn't stop there. Of course, he then wanted to go to an even bigger number, which he then dubbed the Googleplex, as you've described. But his original definition wasn't quite what you said. It sort of converged to that later. But originally, he asked his nephew again, "What am I going to call this? What should this number be? This Googleplex? This is going to be even bigger than a Google." And Milton said, well, it should be 1 followed by zeros until you get tired, which is not, we talked about mathematical rigor earlier. That's not a very rigorous definition because I guess we all get tired at different rates, right? So that's when Kasner obviously came up with the more rigorous definition that a Googleplex was a 1 followed by a Google zeros. And you can sort of go beyond that, of course, and use this idea of recursion. You can talk about a Google duplex, which is a 1 followed by Googleplex zeros, and a Google triplex, which is a 1 followed by Google duplex zeros, and so on. You can really build huge numbers up in that way. But for me in the book, the idea that I really wanted to explore, which is what the book's really about, really, is whilst numbers and mathematics are wonderful in their own right, and like you, Gabe, I did a maths degree. And whilst that's really interesting, really exciting, and there's a beauty to them, for me, I always need to bring that beauty to life in the physical world, if you like to give it some personality in the physical world. So what I've tried to do, and this was something that I really, when I started doing the YouTube videos that I tried to do, is that, yes, you've got this beautiful mathematics, but let's drag it into the physical world and think about it in that context. And so the case of a Googleplex, right? Well, I wanted people to appreciate, well, how big is a Googleplex? How big is it? Well, we can say it's a 1 followed by Google zeros, and that's fine. And that seems big, and everyone's going to agree that's big. But let's really try to feel how big it is. And so I imagine, for example, a universe which was a Googleplex across in, say, meters or inches. It doesn't really make much difference. But a Googleplex across in those kind of units. And I call this the Googleplician universe, and ask, well, what would the property be of such a large universe that's literally a Googleplex across? And I realized that in all likelihood, it would mean that your doppelganger would be out there elsewhere in this vast, vast universe. Now, we don't know if our universe is that big. It may well be. We don't know that it's not that big. It could be. But if it is that big, if we can imagine a universe that big, then your doppelganger has an exact copy of you, Gabe, an exact copy of me, and an exact copy of, I don't know, Donald Trump, whoever, right? Everybody would have an exact copy somewhere else, and many exact copies in this Googleplician universe. And by exact copy, I really mean exact copy. I don't just mean lookalikes. I don't just mean somebody who looks like you but also has the same thoughts. I mean, really exact copy, right down to the sort of quantum DNA, really the exact. So in other words, they're existing in exactly the same quantum state. And you can sort of estimate how far away such a copy would be. And it's significantly less than a Googleplex meters. That's how big a Googleplex is.
Okay, that's great. So we're going to talk a lot about physics and math and their relationship. But this gives us a chance to talk about a different relationship, the relationship between physics to philosophy or religion. So since this thought experiment is about what makes us us, do you think we can be described completely by our physical states? Are we the atoms that make us up? Are we the quarks that make up the subparticles of the atom? can we just be described by our physical states or not? Or how would we even know if that were the case or not?
So it's an incredible question. So of course, in that, I'm making an assumption that there is a quantum state like that can describe you. So what does that mean, right? Even that in itself is something that you can ask, well, how meaningful is that? Because I look at you, Gabe, and you say, well, okay, your atoms are all arranged in some particular way, but there's a lot of information that doesn't really make you not Gabe, right? If I try, I could take an exact copy, right, of you, but I could maybe flip an electron, the spin of an electron around somewhere deep inside your small intestine, right? And is that going to make you not Gabe, right? That seems like a harsh thing to do, right? These are sort of unimportant differences. And so, you know, when I say this is Gabe and that's Gabe, do I really need to worry about the sort of real minutiae, you know, deep inside the thing that makes you, the particular synapse that's going on in your brain, all this sort of, you know, detailed information? Does that really change what it means to be you? And I don't think that's clear, right? And I think so one of the things I did say was, okay, well, let's suppose we're going to really imagine a precise copy of you, as in literally all the electrons, the exact states of all the electrons is the same. Everything's literally the same. Now, the problem with that, even with that question, is how do you actually measure that? Well, to actually tell if I have a copy of you and it's the same, to actually verify it's the same thing, I literally have to measure everything about you. Okay. Now, if I'm going to literally measure the exact quantum state that you're in, there's no option but to absolutely pulverize you. Unfortunately, it's the only way. It's the only thing, you know, literally it would be such an invasive procedure to literally get a little Stern-Gerlach experiment, measure the state of every electron and every atom in your body. And that's, you know, that's not going to be good for you, unfortunately. So the reality is that even in principle, if I was to do that, you would still find doppelgangers within a Googleplex universe. Actually, if I then weaken the concept of a doppelganger and say, well, I don't need to be quite, we don't want to kill the individual in order to verify if they're, you know, to measure the state of them, if you like. We're going to be a little bit, you know, more relaxed than that. Then I could identify a doppelganger as someone who basically just looks a lot like you, you know, maybe even thinks like you, maybe even really it seems like all the atoms are arranged in the same way, but maybe I'm allowing an electron to spin one way rather than another, and I'm not going to worry about those details. Okay, so and if I do that, then actually the distances to your doppelganger becomes much shorter, and you'd get many in a Googleplex universe. So I think that question of what makes you is an interesting one, because of course quantum mechanics means that we can only really get precise information about what you are by measuring. It's the only path to sort of quantum purity, if you like, is to actually measure everything. And if we measure everything, we destroy you. So that's kind of an obstacle to sort of almost answering the question.
Right. And there's also maybe a question about, you know, uncertainty that would maybe affect that. And then also, I mean, you know, I'm okay if a few of my electrons are off. Like, I feel like that would still be me. But like, what makes us us? Is it actually just our atom? Is it actually just this physical state? Or is there something else? And how would you even begin to tease that question apart? If, let's say I encounter my exact doppelganger. I mean, and granted, we could only know that through a very unpleasant exercise of pulling me apart. Let's say I encounter that person. Like, what makes us us? And is that a question within physics, or is that a question that's beyond physics?
Yeah, I mean, I guess I'd have to be agnostic on that point. I mean, in principle, if I believe that there's a quantum state that describes that you correspond to a pure quantum state, in principle, I think most physicists would say that that's likely. Then that describes you. And if I make an exact replica of that quantum state, I mean, there's certain obstacles to that. But if I did that, then or if such a thing were to exist, that, you know, then in principle, that would be exactly you, and it would, you know, I guess we're talking about same thoughts. We're talking about same arrangement of atoms, same feature, everything the same. But then I guess what you're saying is there's something outside of that description which takes you into the realm of theological questions and that kind of thing, and religious questions. I don't know. I guess I'd have to remain agnostic on that. I don't know the answer to that. I mean, I guess it more broadly, which I think is something you want to talk about later, more broadly leads to the question of whether mathematics, and in this case, the mathematics of quantum theory, can describe the universe or could describe a person. Is that enough to describe a person? And, I guess so far we have found that the mathematics does a great job of describing the universe that we see, and we can make amazing predictions and we can do amazing things. But is it going to be enough? And I guess until we find out that it's not, that'd be the point where we have to, that's something we'll give.
Okay, I want to come back to that question. But now I want to talk about a different analogy, which I thought was really interesting in your book, which I hadn't seen anywhere else. So in your book, you talk about two concepts, Poincaré recurrence on the one hand, and the other is Gödel's incompleteness. And so could you briefly describe each of these, and you talk more about the analogy that you've seen between them?
Yes. So for yourself, with a mathematical background, you probably heard of Gödel's incompleteness before. I mean, very loosely, I like to describe it as there are more questions than answers, if you like. And it's the statement that, that there are, you start off with some rules, some axioms of your sort of, your mathematical framework. And you can build statements that are true, that they are true statements, but they can't be proven to be true within that framework. You might have to enlarge the framework to prove that they're true. Okay, so they are true, but you can't prove them within the language that you give. And if you like, an analogy might be that there's a statement that is true, but you can't say it in English. You can't say it in English or something. It just can't be done in that language. You have to go larger to be able to describe it. So there's this idea within mathematics that given a set of rules, you can have statements which are fundamentally true but can never be proven with that. And it's the mathematician's nightmare, of course, because you can be you might not know whether this thing you're trying to prove, maybe, I don't know, it can be, the continuum hypothesis or something. The thing you're trying to prove, is it provable? It might be true, but it might not be provable within the framework. You have the framework which can describe it, but that framework might not let you prove it. And so that's kind of, you could spend your entire career trying to work on it, and then it's just not doable. And that's be an absolute nightmare. So that's Gödel's story, named after, of course, Kurt Gödel, the great logician. On the other hand, we have this idea of Poincaré recurrence, which is something that we're sort of, again, it's something that you sort of associate with finite systems. And it says that, you have any finite system, and then you can sort of have random jumps in that system. Then eventually you'll always get back to where you started. So let me give you an example of that in action. So, for example, you take a pack of cards. So you take a pack of cards, and normally when you buy a pack of cards, they're all arranged really nicely in order of suit, and in order, ace, and 2, 3, 4, and so on, right? So they're all arranged beautifully. And then you start playing, you start shuffling the cards, randomly messing them up. Okay. If you shuffle for long enough, and it's a very long time, and that each shuffle is truly random, then eventually the cards will arrange themselves once again in that perfect order. They will get back to where they started. That's the Poincaré recurrence. You can think of it in the terms of a body of gas. So you could have some gas that's stored in the corner of a room, and then it distributes around, and it sort of has this random fluctuations, this random motion of the gas particles. Then eventually they'll after a very long time, end up back where they started. This is the notion of Poincaré recurrence. Now, the idea that I explore in my book is that our universe is a finite system. Okay, so one of the things that we believe is that now we're entering this era of what we call dark energy domination, where the universe is entering this sort of phase where the expansion of the universe, so you think of the expansion of the universe, of galaxies, going, the space between galaxies getting bigger and bigger and bigger. Now that space between the galaxies is getting bigger and bigger and bigger, but it's actually accelerating as well. So it's getting bigger faster, which is counterintuitive because, you think gravity is supposed to pull things together, but actually it's getting faster. And that's due to this thing called dark energy. And our best way of describing this leads us to believe that actually the universe may well be a finite system. Our patch of the universe will be a finite system. In other words, a number of sort of degrees of freedom that you need to describe it is finite. It can only be in a finite number of states. And so it's like a giant pack of playing cards. So you shuffle that pack, and it doesn't matter. Eventually you shuffle. Then the universe you can start out now, keep shuffling, keep changing it, and eventually you'll get back to the state it's in now. The universe will effectively reset itself, find itself once again in the state we're in now. Now, that happens over a very, very, very long time scale, because basically, even though it's a finite system, it's a very large system. So our universe has a Poincare recurrence of about 10 to the 10 to the 122 years. So it's a very long time. So this is something that we believe to be true, but you can now ask yourself the question.
That's more than a Googleplex.
It is more than a Googleplex, yeah. So it's a very, very, very long time. But now you can ask yourself the question, could anything ever measure this happening in our universe? And the reality is it couldn't. And the reason is you can invent a device. Let's suppose you invent a device which measures the state of the universe. Okay. And then it keeps measuring the state of the universe. And the hope is that one day it'll measure the recurrence happening, right? It'll measure the fact that the universe got back to where it started. But the problem is the time scale is so long that the device will undergo a quantum instability. It'll effectively quantum break before it ever gets the chance to measure the Poincare recurrence. So it feels like, when I thought about this, I felt it sort of intuitively seemed very similar to Gödel's incompleteness, in the sense that you have something which is true, the fact that the universe is going to get back to where it started, but nobody's ever going to see it happen. You can't prove it. There's no experiment you can do that can show it, because any device that you built to try to measure it will break over that kind of time scale. And it feels a little bit like a physicist version of Gödel. Well, maybe it's not really a physicist version. Maybe it's a mathematical physicist version of Gödel.
Okay, great. So that leads directly to the next question. So I wanted to ask you about string theory. So there's a lot of people pursuing beautiful theories here, but there still haven't been any that are testable. So is what string theorists are doing, is that physics, or is that something else?
So I think this is obviously something you see crop up a lot in a lot of the debates about physics and theoretical physics in particular. And I think the first really important point to realize is that when people say things about, oh, string theory isn't testable, they're really making a much broader statement, although they never say it this way. And that's that actually quantum gravity is what they're saying isn't testable. Any theory of quantum gravity. See, the problem is when we want to, string theory is claimed to be a particular candidate for a quantum theory of gravity. So in other words, a theory of gravity like general relativity, but which also in which we can throw in quantum mechanics and we can make sense of very, very strong gravitational fields up to arbitrarily high energies. And so this is what string theory claims to be. And there are other rival theories that also claim to be it, like loop quantum gravity, for example. Now, the problem is that experimentally, you only expect these quantum gravitational effects to kick in at really, really, really high energies, way beyond the sort of reach of the kind of collider experiments we do in Geneva, at CERN, or at the LHC, for example. And so because of that, this is a problem. So these energies of these experiments are so high, they're inaccessible the energy of quantum gravity is so high, it's inaccessible to any of these experiments. And that situation is not going to change anytime soon. So in that sense, any theory of quantum gravity in that sense is untestable. So it's as true of loop quantum gravity as is a string theory. And yet for some reason, those proponents of loop quantum gravity seem to use it to attack string theory when it could equally apply to themselves. Now, what I would say is that there is one possible probe for quantum gravity, and that's primordial gravitational waves. So one of the things we're looking at in the cosmic microwave background radiation is for tensor modes, what are called tensor modes. Now, those are essentially gravitons in the early universe, and that's what we're trying to measure. And those really are quantum gravitational phenomena. So that is a window into quantum gravity, and the details of that are a way to test any theory of quantum gravity, not just string theory. And so it's not completely inaccessible to experiment, but it's not easy, I think is the point.
Okay, so maybe if there's time, we'll come back to that question, because it seems like also what you were doing there is you're saying, okay, that's a fair criticism of string theory, maybe, but it's actually also going to have to be equally applied to any quantum gravity. Am I using that right?
Completely right.
In which case, you could then lodge the same critique of any theory of quantum gravity, which is that is any of this physics if it's not testable? But then you're saying, well, maybe it is testable. Maybe.
Maybe we'd have to get lucky. We'd have to get lucky and find primordial gravitational waves. Now, whether there's some other clever experiment that somebody can cook up that can find a signal of these things, I don't know. There is another important point, and this is where I think string theory. You could argue that string theory is being tested in a way, or at least the foundations of string theory is being tested. So string theory is very much built on the logic of quantum mechanics and relativity, those two really core ideas of 20th century physics. You take those together and you're very naturally led towards ideas related to string theory. If either of those is found to fail an experimental test, either of those core pillars on which string theory is built, so quantum mechanics or relativity, if either of those fails, then forget about string theory. There would be no motivation for following string theory if either of those two pillars were to fail. Now, of course, that's finding no problem with those two pillars doesn't mean that you definitely have string theory, but either of those pillars falling would take string theory down as well.
Okay, well, maybe we'll come back to that too. But you mentioned getting lucky. Okay, so what do you think of the so-called unreasonable effectiveness of mathematics in the natural sciences? So in your book, you talk about the concept of naturalness as a sort of, and here I'm totally paraphrasing, I'm not sure if you use these words, but as a sort of smell test or a sort of intuitive judgment of a theory. So is the efficacy of mathematics in the natural sciences unreasonable, or is it expected? And could it be any other way? Or is nature, in fact, unreasonable, actually? And if it couldn't be any other way, then the question is why? And someone like Newton would have had an answer to that, which is that God designed the universe in a nice way. So what do you think?
I think it's an incredible question. So, of course, I mean, you started off by quoting Wigner, the famous Nobel Prize-winning physicist Wigner, who wrote this wonderful essay. I think he gave a talk as well in the early 60s, late 50s maybe, on the unreasonable effectiveness of mathematics. And it is, and actually that article, it starts off with a joke, right? It starts off with this joke about, I think there's two guys and they're talking about physics and maths, and one of them says, well, shows him a population trend, and he shows him the Gaussian distribution. He says, look, and then the guy goes, well, what's this symbol here? And the symbol is pi, right? So he goes, well, what's that? Oh, it's pi. He goes, well, yeah, what does that do? Oh, that relates it's got stuff to do with the circumference of a circle and relating it to the diameter. And it's like, what's population trends got to do with circumferences of circles? These are two very disparate ideas, and yet they're using the same pi, right? And I think it's true, right? That it's in a way amazing. It's absolutely amazing how effective maths is in the physical world. Like physics is our goal is to try to describe the universe we see, and the tool that we use is mathematics, which is absolutely 100% a man-made construct, right? It seems to be. And so our universe seems to use this, and we've been so effective in describing the laws of nature and the physical phenomena that we see using this amazing tool that we've created, which is maths. And even when it seems to, even stuff like imaginary numbers, like, whoa, imaginary numbers, not even real numbers now, like things like the square root of -1, these are not even real numbers. And yet, when you start writing down the physics of electrons, for example, it's got square root of -1 sitting in there. And so this is amazing, right? So there is this unreasonable effectiveness in mathematics, and it hasn't failed as yet. But then you have to beg the question, right? So is it ever going to fail? Well, let's imagine that it will never fail, right? Then you have to ask, well, so let's say mathematics will always describe our universe. Let's imagine that is the scenario. But even then, you're faced with the question, well, will the universe use all of mathematics? But then you end up with Gödel questions, about Gödel incompleteness questions. But even like, why is some of the, let's suppose it seems unlikely that the universe would use all of mathematics. For example, would it use infinite, transfinite mathematics and stuff like that? Would it use that? Maybe the universe is finite, fundamentally finite. Maybe it only ever uses finite maths. That's an obvious sort of barrier, sort of threshold that you can imagine. And then you have to ask, well, this other maths exists, and yet the universe isn't using it. Why not? And that's a really deep philosophical question, I think. And it's not one that I necessarily know the answer to, but you'd have to ask that question. Why is it choosing this maths and not this maths? Or maybe there are physical phenomena for which mathematics fails. And sometimes it's kind of this idea of this effectiveness of mathematics is really powerful. Now, if we take it seriously, then the power of mathematics in describing the physical universe, then we can overcome some of those problems of experiments being too far away from us. So we talked about quantum gravity and trying to test quantum gravity using standard empirical methods. Okay, and that's really difficult because the scales at which quantum gravity becomes important, the energy scales are so high, so beyond the realms of modern experiments, you just can't do it. Unless you get lucky with the cosmic microwave background, but we don't know if that's going to happen or not. So if you can't use standard methods, but you're still interested in the question of what is quantum gravity, and you should be interested in that question because it's related to how the universe began, for example. That needs knowledge of quantum gravity. Then the only other tool you really have available to you is mathematics. Now, admittedly, that requires you to say, well, the universe is going to remain mathematical. Okay, but if you accept that and you use mathematics and mathematical consistency to push your theoretical models to higher and higher energy, and if you can argue that they do so in a unique way, then maybe you can sort of gain an understanding using the power of mathematics on what's happening with quantum gravity. Now, this wouldn't be the first time that in nature that using mathematical logic led us to the right theory. Even going back, for example, to Maxwell when he developed his laws of electromagnetism. Well, there are laws that have been laid down by Ampere and Faraday. And what Maxwell did is he took those laws and he realized they didn't make sense mathematically. They didn't quite align with the laws of calculus, right? So he used mathematical logic to say, well, hang on a minute. This doesn't really fit with the maths, I believe, perhaps he didn't said that, but if we believe the universe is mathematical, then it has to. Right? It has to be mathematically consistent. So let's make it mathematically consistent. And in doing so, he developed the theory of electromagnetism that we now know holds true. And as a result, and then that comes with its own predictions, which are then tested. He developed the idea of sort of, light being a sort of electromagnetic wave and all that wonderful physics that's emerged from that. And yet it really came from saying, well, I'm going to assume the universe is mathematical. And then I have to make these laws mathematically consistent, and lo and behold, it works. So it seems that it has a history of working, and yet somehow, how far can we push it? We push it until it fails, I guess.
So your answer basically is it's worked so far.
I think that's in a sense, that's the empirical evidence that we have, right? That's you can apply that empirical logic, right? That is mathematics a good tool for describing the universe? Yes, and it is until it isn't. And you can apply that. You go back historically, maybe people take a more religious angle. The sort of religious ideas were describing the phenomena they saw until maybe that didn't quite work, or they found another way. Right now, mathematics is a really powerful tool we have for describing physical phenomena. And until it fails us, you'd have to argue strongly for some alternative tool. And at the moment, for some questions like quantum gravity, it may be the only tool we have unless we make a dramatic breakthrough in our understanding of experiments.
Okay, great. So you end the book with a sort of rejoinder to the famous mathematician G.H. Hardy. So Hardy was a number theorist who famously wrote a defense of mathematics for its own sake in his essay, A Mathematician's Apology. Your book ends with a reply to Hardy that a certain number, which you could tell us about, he had once worried was boring, was in fact, actually, and I'm quoting you, bloody fantastic, just like every other number. So what do you think of Hardy? And I don't know if anyone has ever written a physicist's apology. Is that because the answer is obvious and there's no need to write a physicist's apology? Maybe we need a mathematical physicist's apology?
Obviously, physicists shouldn't have to apologize for anything. But actually, I don't know about that. Okay, so confession time. I do actually have there it is, mathematician apology. I do. It's a bit dusty, which suggests I haven't looked at it for a while. So that should probably tell you what I think of Hardy. Hardy's great. You know, and his other book, which I actually have as well, which is in the office of work, is one on divergent series, which of course has and his interactions with Ramanujan and all the wonderful ideas about sort of, you know, infinite series, you know, infinite sums, like our famous sum of the integers, which kind of brings us back full circle, right? Yeah, so I think, you know, Hardy was trying to justify the pursuit of mathematics almost for its beauty, and I think this is what I think is important in understanding is that I think there's clearly real value in that. And as somebody who's kind of driven by that beauty and that love of mathematics, you know, it is true that has led to sort of, you know, improvements in understanding of the physical world that come much later. So sort of ideas associated with mathematics and brilliant, wonderful ideas like imaginary numbers, right? For example, being a classic example, imaginary numbers are necessary to describe the physics of electrons. Okay, so you have imaginary numbers. So somebody decided, well, what happens if I take the square root of -1? That doesn't seem to fit the rules. Okay, let's make some new rules. Let's figure out. Let's expand mathematics. Let's expand this beautiful subject. And then much later, you develop these ideas associated with electrons, and electrons need it. Similarly, you know, Bernard Riemann and all his ideas about geometry going back, you know, in the 1800s and so on and so forth, all these deep ideas just about geometry, he was just pursuing that for its mathematical interest, for its mathematical beauty. And yet later, Einstein comes along and rekindles all these ideas and develops general relativity and the ideas about space-time being curved and that being the true nature of gravity. So I think there's always a good reason to follow your nose when you see something is beautiful. That's not a proof that it's going to have an application, but, you know, as humans, our world, you know, we're drawn to beauty. We're drawn to, you know, musical elegance, for example, and that kind of thing. And that can also be present in the mathematical world. Absolutely, it can. And if somebody uses it for something really cool later on, that's even better. But it doesn't even matter if they do or not, I think. Now, in terms of a mathematical physicist's apology, well, I guess we'll apologize until there's no need to apologize until we have to, I guess, right? I mean, I think that trying to understand the physical world is a really important question. And as I said, talking about things like questions of quantum gravity, well, the question of quantum gravity is related to like I said, it's the beginning of the universe, right? Because one of the things we know is that as you go backwards in time and the universe, the expansion of the universe sort of goes into reverse. So in other words, it's shrinking. Eventually, the conditions of space and time become so distorted that you need a quantum theory of gravity to describe them. So when you're talking about question of a creation of the universe, you know, you're talking about quantum gravity. And that's where we really, you know, these are really fundamental questions that sort of not only ask the question of who we are or why the universe is here. I don't think there's a deeper question than that. And I'm not ready to apologize for asking those sorts of questions. Maybe in the future.
Okay, so maybe let's get a little bit technical and before we go to an audience question, which is, I'm going to quote you. You say, some people are trying to mathematically prove that string theory is the unique theory of quantum gravity. So if they're successful, we no longer need to test string theory directly with experiment. We just need to test the assumptions that went into the underlying mathematics. Okay, so first, what's that theory called? Second, would physics really be content with that? Or would they want more experiment? And mostly, can you just explain that?
Yeah, so the idea that is that it goes back to what I said earlier about these two pillars of 20th century physics, quantum mechanics and relativity. So if you take those two key ideas and you and then you ask the following question. I want my theory to respect those two key principles. And at the same time, at very, very low energies, it should look like Einstein's theory of gravity. Let's make those our ingredients. So it should respect quantum mechanics, it should respect relativity, and in the sort of everyday world that we experience, it should just look like Einstein's theory. Now, can I extend that theory all the way up to arbitrarily high energies and into this quantum gravity world, right? Whilst respecting those two pillars. Now, those pillars actually place very strong constraints on the theory. And in particular, if you demand something called weak coupling so that no sort of things don't push and pull on each other too hard, which is one of the things that allows you to sort of do calculations, actually. If you demand that that remains true, then there's a very natural way that from general relativity, respecting these rules, you very naturally go to sort of string theory. There's something called a scattering amplitude. So when you sort of fire two gravitons, bash them into each other and then scatter them. Okay, you can describe this process in general relativity. You can describe what it looks like at low energies. You can then say, I want to consistently push that process to very high energies. And then there's literally a mathematical rule that you can write down that it has to obey. And you can come up with a formula for this process. And that formula is the formula you get from string theory. The question you can ask yourself is there any other formula which obeys all the same rules, that as in it gives you the results of general relativity at low energies, and it obeys these two pillars of relativity and quantum mechanics? Now, if you can prove that there is no other mathematical formula that obeys those rules, then you've kind of proved the uniqueness of string theory as the only path towards quantum gravity. And people are working on that. So in other words, what it's like saying is I have these two pillars. I have this thing that I want to achieve at low energies, and I want to see what I can put on top of the pillars. Okay. Is there only one mathematical object I can put on top of those pillars, or are there many? Now, as it stands, there's only been one found. Okay. And can we prove that it's unique mathematically? And people are working on that idea, and it's a really interesting direction of study.
Is there a name for that theory? Is there a name?
No, string theory. String theory is so what we have is we have one example of where we know what to put on top of the pillars that obeys all the rules that we apply. We say, right, we want to get general relativity, we want to obey quantum mechanics, we want to obey relativity, and we want to have this weak coupling where things don't push and pull too hard. We put all those ingredients in. We have an answer which is string theory, which is consistent with string theory. The question is, are there any other consistent answers with all those ingredients? At the moment, we don't have one, but we can. It's a mathematical question. That's what's really nice about it.
Great. I think that sums up a lot of the questions so far. So we have I want to go to a question from the audience from Marco de Souza Acevedo. Is Poincaré's recursion contradictory to the second law of thermodynamics, like the law of entropy? Because, I mean, and I was sort of thinking that too. I mean, you talked about the gas kind of going back into the corner, and that doesn't really happen. But like, right, so talk about that.
So I think I have to be clear about what entropy is there then. So entropy is when you don't have full knowledge of the system. Okay, so we're comparing having precise knowledge of the system to not having precise knowledge. So when you talk about entropy, it basically says, have some system, which is let's say a macroscopic system, as it generally will be, and I can sort of measure certain quantities like the temperature, the entropy is one, and there can be lots of different arrangements of that system which yield the same macroscopic property. So take an egg. I look at an egg, right, and it's an egg, right? Now there might be lots of different quantum states which describe the same egg. Lots of different arrangements. Forget quantum mechanics. We can do this classically. There can be lots of different arrangements which describe that egg that literally, for as far as our macroscopic measurements are concerned, just mean the egg, right? I don't need to. There's missing information. There's details I don't worry about when I define it as an egg, as the egg that I'm interested in, at a given mass and temperature and so on and so forth, right? And so what entropy is when you talk about these macroscopic things, and you're basically, you have missing information. You've got the number of ways which describe the same egg. So there might be a Google ways in which you can arrange the atoms, and it's still the same egg, right? That's because we're not measuring things with this level of detail. When I'm talking about the Poincare recurrence of our universe, what I'm actually imagining is it comes back to this. I'm assuming there's a precise, pure quantum state of the universe, right? I'm actually saying there is one, right? Now, there could be many. The universe could have up to a huge number, but I'm assuming transitions between the precise states. So no, in that sense, you're not really sort of averaging over lots of states. So I don't think there's any contradiction with the second law of thermodynamics in that sense.
Okay, great.
I hope that's a clear answer, probably clear as mud.
So second law is not violated.
No, the second law is not violated. No, it doesn't even make sense to ask about the second law in that context, because you're not talking about an average, a system where you're averaging over lots of degrees of freedom.
Great. So Ryan Garati asks, your love of math is clear, but is there an aspect of math or of theoretical physics that has just never sat right with you? So something that seems wrong, or maybe you just don't enjoy working on it.
That's an interesting question. Okay, I'm going to tentatively say infinity. So I wrote a whole chapter on infinity in my book, and don't get me wrong, what Cantor did with infinity is elegant and beautiful, and it would be incredible if that had some relevance to our, as a theoretical physicist, to our physical world. My hunch is that it doesn't. My hunch is that there is no room for infinity in the physical world. I could be completely wrong about that. There's no experimental evidence either way to say whether it is or isn't. This is just I suspect that one can do the physics of our universe without any reference to infinity. Now, of course, we do things in theoretical physics where we encounter infinities, and actually one of the when we talk about quantum gravity, we're trying to overcome the infinities that occur in a quantum theory of gravity. But that's precisely it. We're trying to overcome them. We're trying to get around them. We're trying to avoid them, if you like. When we did quantum electrodynamics, the infinities that were encountered there, we kind of skirt around them. We avoid them, and it really feels like they're not really there. I don't think they're really there. It's just we're using these mathematical tricks to skirt around them. And so, I think a better understanding of how nature avoids infinity would be really, really nice, actually. And this comes back to, again, we're doing full circle here to this sum of the integers, actually. And is there a real way to understand why that's, if it really is minus a 12th, and how somehow we avoid that dreaded infinite? And is string theory and physics somehow doing that, and we just haven't figured out how? That's a really deep and interesting question I'd love to know the answer to. So I'm going to say infinity is the maths which that I want to avoid, but it's still beautiful maths.
Okay, but then to follow up, a lot of your book is about these numbers that are so enormous that there's no, possible way that, like there would be just an energy crunch if we tried to somehow imagine them in the universe. And, and the numbers get much bigger than that. And so, if you follow that argument, then wouldn't it be the case that you are just sort of led to some sort of ultra finite position where you not only reject infinity, but you just reject all these big numbers?
Right. Okay. So you're saying, like, is there just a biggest number which nature will ever encounter? That's a cool question. I don't know the answer to that. I mean, maybe. I guess if you're going to say it's finite, then yeah, right. If it's finite, then there's probably by that very definition there has to be a largest. But yeah, that's a really interesting question. That's not something I hadn't thought of it that way. But maybe, yeah. I mean, of course, in some sense, what I was trying to do in the book was just take these crazy big numbers like Graham's number and just by bringing them into the physical world, really ramming home how crazy big these mathematical constructs were, and how, in some sense, they have no room in our physical world. That's the message of the book, in some sense, because you try to squeeze them in, and all hell breaks loose.
Great. Okay, so the next question is from Nafis Zebojadi. So you're infamously a huge Liverpool fan. What's your favorite math physics problem related to football?
So you should be able to see the badge there. It's the Liverpool. This I was given this by my nephew who actually plays Liverpool. Math problem related to football. That's a good question. Of course, when I describe entropy using Premier League tables in my book. I don't know. I mean, I did a video once about the World Cup, the Jabulani footballer used at the World Cup. Which really moves sort of spectacularly in the air because the sort of, the fluid, how the fluid flows over the book. I would say that, but the video I did, I actually went in goal and I was really rubbish in goal in the video, and everybody commented about how poor I was. And it wasn't my fault. I had a bad back on the day, so I thought it was really harsh. But they didn't know I had a bad back. But so maybe that. But obviously on the actual video, I have bad memories.
So we're getting close. I wanted to ask you about another relationship between math and physics. So when I started reading your book, I didn't realize that it was going to be a physics book. I thought it was going to be a popular math book. And so when I began it, I was surprised to see that there was not any mention of the primes, or at least it didn't begin there. And so the prime numbers, have a historic importance in mathematics and in computer science with cryptography. Do physicists care about primes?
Absolutely,
really?
yeah. There was almost a chapter that I wrote, which I never ended up doing, but it was a topic that I thought about including in the book, but which never made the final cut. And so probably what I'm going to say is going to be poorly researched as a result. But there's a relationship between primes and the distributions of primes, and for example, the energy levels of the heavy atoms. So that's something that's really weird, and I don't think it's fully understood. And yeah, there's something strange going on there. There's this Wigner famously looked into this, but yeah, there seems to be this relationship between prime numbers and how they're distributed, and the energy levels of heavy nuclei. So yeah, that was one area.
The Riemann zeta function is coming up again, I guess, in this whole conversation.
Right. Okay. I mean, that's another one, actually. Of course, you could bring the Riemann zeta function and how that relates to, of course, the prime numbers, and how that relates to sort of in string theory, for example. We use the Riemann zeta function to sum the integers. I mean, there are other ways to sum the integers, but the Riemann zeta function is one way. And in string theory, the where that becomes important is in figuring out how many dimensions there are of space-time. And I think I'm right in saying that string theory is the only theory I know of where you get a prediction for the dimensionality of space-time. Maybe that's not quite right, but it's certainly the most famous one. And we normally say that there are sort of 3 dimensions of space and 4 of time, and 1 of time, making 4. Now string theory, of course, predicts 10, and the 6 of them are wrapped up very, very small. But indeed, it's summing up those integers, and which you maybe use the Riemann zeta function, which again is related to prime numbers, which gives you that answer ultimately. And so yeah, it's primes are lovely. I mean, everybody loves a prime. So yeah, but the big one is that Wigner thing with the energy levels of the heavy nuclei. There seems to be something funny going on there, which is certainly something I would like to think about and read about more in the future. But yeah, it was there was going to be a whole chapter on that, but it never happened. So maybe that's for another book.
Okay, we're really close to time, but maybe I'll sneak one last question in, which is just that one of the primes that caught my eye in your book is a favorite of mine, the number 17. You discuss the wallpaper groups in the book. Maybe there's not much time to talk about what those are, but hopefully you could describe a little bit about that. And just does this number of different wallpaper groups itself have a corresponding physical significance? Does it have a corresponding statement in physics?
So the idea is that these wallpaper groups is you have these kinds of patterns. I don't know, like a threefold rotation or some sort of translational pattern, and you can ask how many ways are there that you can sort of sew together these patterns and make like a wallpaper, and that the pattern repeats in a consistent way. And you might think there's an infinite number of ways in which you can do these sorts of things, but there's not. There's just 17. And that's why when you look at Islamic art, for example, in the Alhambra and places like that, there's only 17 patterns, really, of these consistent mathematical patterns that emerge. And that's because it's been proven that there can only ever be 17. And the reason there's only so few, why it's 17 and why it's prime, I don't know. But the reason it's so few is because you're trying to sort of, when you have symmetry, essentially what we're talking about here, when you have symmetry and you try to merge symmetries together and tie them together and align them, then that very much restricts what you can have. And there's a definite analogy of that in physics, is that, symmetry drives physics, but bringing those symmetries together and aligning them very much restricts the kind of physical theories that emerge. That's not saying it's got anything to do with prime numbers. That might just be a fluke in this case. But I don't know. Maybe there's more to it that I haven't appreciated then. But yeah, that's what I think that those connections are made. At least that's what I explore in the book.
Okay, Tony, thank you so much for taking the time to talk with us and share your thoughts about math and physics and philosophy and the universe. If you want to find out more from Tony Padilla, read his book, Fantastic Numbers and Where to Find Them. Tony, okay, as our last kickoff question, we talked a lot about fantastic numbers, but I'm not sure we actually asked this question already. So do you have a favorite number?
Yeah, let me say 6, because it's the number of times Liverpool have won the European Cup, but hopefully that number will go up over time.
All right. Thank you, Tony.
Cheers. Thanks, Gabe.